Up next to present, we have Jayson Boubin from the State University of New York at Binghamton.
All right. Let's see if I can figure this out. Looks like I can. All right. Hello, everyone. My name is Jayson Boubin. I'm an assistant professor of computer science at Binghamton University. Might be the first computer scientist to speak at a conference like this, maybe not, but I'm really happy to be here. And I want to talk to you a little bit about my work. So I work with UAVs, particularly autonomous UAVs. And I want to talk a little bit about the opportunities for autonomous UAVs for spotted lanternfly detection and mapping. Let's see if I can move forward here. Green button? Oh, big green button. All right. So first of all, I want to do a little audience poll. Does anybody here use UAVs at all in your work? Anybody here? Okay, good. That's a pretty good number. So most people, in the regular population view UAVs as either toys or weapons, right? Maybe there's something your kids have, or maybe there's something that are used, for terrible means. And I like to think of UAVs differently, right? And those of you who use UAVs for this kind of work will know that UAVs are extremely useful. They have a very high sensing capacity, which means that we can put very interesting sensors like regular cameras, hyperspectral cameras. We can capture near infrared data. We can capture, we can use magnetometers, lots of interesting sensors we can put on these things. And not only can we sense information from these devices, we can also actuate. We can have the UAVs manipulate their environments, use a robotic arm or collect samples. We can have UAVs coordinate. They can talk to one another. They can communicate. We can also instrument onboard intelligence. We can use artificial intelligence on board these devices, which is where most of my work lies. Now, it's important to recognize that UAVs are useful in some situations, not useful in others. Now, UAVs are particularly useful when we're covering relatively large areas. So something like a large crop field, which is where I spend a lot of my time, UAVs can be very useful. They can cover areas for, say, crop scouting much faster than a group of people. And they can coordinate as swarms to parallelize their environment. If we need very high resolution for sensing, let's say we need some very, very small ground sample distance to calculate, to determine if this is a stink bug, or this is a spotted lanternfly, or this is some specific disease, then we can get that with UAVs. We can really get up close and personal. And we can use UAVs when environments are dangerous or hard to access, right? If there's a wildfire, if there's a brush line, we can get over that, or we can get around that wildfire with a UAV somewhere a person might not be able to get. Now, UAVs are also not the right tool for many, many, many situations. If we have a very large area, like an entire city, or if we're trying to map the entire world, right? We should probably use a satellite, or use something flying a little bit higher in the air with a little stronger camera. If our ground is clear, or we don't really need aerial maneuverability, it's much more beneficial to use a ground robot. And we see a lot of this specifically in viniculture. And that's because ground robots are about 2 orders of magnitude more energy efficient than UAVs. UAVs are very energy inefficient. And if areas already have existing infrastructure, then why not just use a fixed camera, right? So we really want to use UAVs in situations where we are sensing some small and complex phenomenon over a relatively large and poorly provisioned environment. So if that sounds like something that you're familiar with, then maybe you're taking my point. Now, most of my prior work is in agriculture. So I make autonomous UAVs. So I'm a roboticist and computer scientist, but I spend a lot of my time in applications in agriculture. So I'm from Ohio, and we have lots of problems in soybeans with stink bugs and Japanese beetles. And so what we do with our UAVs is we have them detect these things like leaf defoliation, or the beetles themselves, scorch, mildew, et cetera. And we have our UAVs actually learn crop fields. So we fly swarms of UAVs, or we have swarms of UAVs fly themselves over crop fields for weeks or months, learning the fields, detecting and mapping these phenomena with machine learning, ultimately producing maps that we can use either to provide the farmers with information, or to apply treatment via UAVs. Now, looking forward, so I said I'm from Ohio, and I moved to New York to accept a position at Binghamton University. I was talking to many people in New York State government, and they're very, very concerned about the spotted lanternfly, right, as we all are. And so I thought, can I use autonomous UAVs, the stuff that I've worked on in the past, in a way to help this problem? And so I thought that UAVs have a number of particular advantages over the regular methods that we use to identify spotted lanternfly populations. Particularly, they can fly very high in tree canopies. Right? We know that it's very difficult to detect spotted lanternflies in tree canopies, and in the Penn State Extension mitigation manual that's you can find out there, there's a very nice stat where 2%, only 2% of egg masses sit below the canopy or in a reachable area within the tree. So if we can detect those with a UAV, we can have something that can fly up into the canopy and see them more easily. That might be a significant benefit. Now, we also know that egg masses are stationary. They sit there for 6 months, particularly the 6 months of the year where the canopy is most defoliated. That's another strong advantage. Now, UAVs can generally cover areas much faster than humans, and they can fly over underbrush that's regularly present near, say, roadways or rail lines where we see lots of spotted lanternfly spread. So why am I here? What am I talking about? Well, the general idea is that we know that spotted lanternfly reporting lags behind spread. So as these bugs are spreading, we can see things like, from prior work, eDNA hits in areas where spotted lanternflies haven't previously been reported. And it can be very hard for responders to actually go out and map these spotted lanternflies, for people like you to actually go out there. And so our goal here is to view autonomous UAVs or use autonomous UAVs as a layer of rapid response. So can we take UAVs, go out there, fly into tree canopies in areas where we suspect spotted lanternfly populations may be, for early verification and quantification of populations? And so the general idea is that we want to navigate forests without crashing with these autonomous UAVs, actually identify not necessarily spotted lanternflies, but egg masses in particular with those UAVs via machine learning, and then produce maps that can be used for mitigation efforts. So a little bit more detailed approach here. What we're doing is actually collecting piles and piles of data on spotted lanternflies, actual images of spotted lanternflies, images of egg masses, images of nymphs. And we're training right now quantized neural networks that we can put on board our UAVs to actually have them detect spotted lanternflies through camera feeds. We've been able to do this for over a year now. Actually, my students got their first neural network working on a drone, I think last February. So we've got a very nice neural network that works, relatively accurate, about 95% accurate in our testing sets. And what we're doing is working toward deployment. We're working towards actually putting this on a UAV that we can send out into the real world, that can navigate its environment properly, to ultimately fly as one of a swarm of UAVs, a group of UAVs that can actually navigate a forest and ultimately build maps to track these flies. Now, one question you might have is, how do we actually do this? How do we detect things? And I want to just talk a little bit about this. So we need data because any sort of machine learning effort necessitates data as a predicate. So we need classes. We need data that represent a class of spotted lanternfly adults, of egg masses, but also data that represent things like nothing. Oh, this is just a regular tree or a regular environment. We want to be able to differentiate between an adult spotted lanternfly and an egg mass, and also things like a stink bug or another bug that might be out in the environment. What we do is we take thousands of these images, absolutely thousands, maybe tens of thousands or millions if you're training a very large, very complicated network, and we pass these into our mathematical model. So neural networks are just math. It's really just a bunch of math. And in this case, we use convolutional neural networks, which take little pieces of the image, call them kernels, maybe a 5x5, 3x3 area of the image. We break our image up into many, many smaller pieces. Then we break those pieces up into pieces, maybe take out the middles, maybe average them all together. And ultimately, we turn each one of those into a feature that we pass to a fully connected neural network, where each neuron in the network is just a mathematical object with a weight and bias. That's all we do. We multiply the weight by the input from that little kernel. And we figure out how we did, right? We return a result of 1 or 0. Is this an egg, or is this an egg mass? Is this a spotted lanternfly? Is this just nothing? And we figure out how we did, right? That's all we do. We figure out how we did, and if we did poorly, which we often do with these neural networks, then what we do is we use a little calculus to figure out which neurons were responsible for that incorrect calculation. We update them just a little bit. We do this over and over and over and over again, many thousands of times, until we get a good result, until we're good enough to the point where we can actually say, okay, we're 95% accuracy. Let's deploy this. Let's test for generalization, see if it works in the real world. Now, if we have a model, that's not enough, right? I can't just take my phone out or my drone out and fly it and say, oh, it's going to be fine. I need to have some sort of layer of autonomy. I need to have my drone not crash into the trees that are it's trying to navigate. So the way that we generally do this is via something called simultaneous localization mapping, or SLAM. Now, the idea behind SLAM is that we use two interesting mathematical features. One is that we use stereoscopic cameras. So we'll take two cameras on board a drone, and we'll calculate a depth map in front of the drone. So for every, for a normal image, you would just see red, green, and blue defined pixels. In this case, we have red, green, and blue, and also depth. We can know how far away a pixel is from us by a parallax from the two cameras. Now, that's not enough, though. Just knowing how far away we are from something, it's not sufficient. We also want to know where we are in our environment. So we can define features of our environment using, again, little mathematical objects. In this case, you can see a picture of a church window. That corner of that window is something that would be defined as what's called an orb feature. That just means its rotation, translation, scale, and variant, meaning that we can track it no matter where our drone is, as long as we can see it in the image. We can track that feature and many other features in a three-dimensional point cloud that we can then associate with our depth camera results to build a map and localize within the map. So we can do this, and we can do this in forests. And what we're trying to do is take these two aspects, things that we're currently developing or that we've already developed, take our neural networks, take our autonomy, and then actually deploy these. And so we're targeting a deployment. We have a few sites that we're thinking about. Blue Marsh Lake near Reading, Pennsylvania, just down the road, is a place that we've been in discussion with. And we're thinking about deploying, hopefully, somewhere next winter. So around this time next year, hopefully I'll be here with some results. But the reason that I'm here, really why I want to talk to you about, is that we need some help, right? I can't just come into this community. As I said, I'm a computer scientist, not an entomologist or biologist. And I want your feedback, and I want information from you. So if you have, for instance, data, if you have spotted lanternfly images, Brian put it very interestingly in a call we had the other day that many of you might have more pictures of spotted lanternflies on your phone than you do of your kids. And if you do, I mean, we would love to use them. And we're very interested in building a community-driven data set so that people can actually train machine learning models to detect things that are useful for society and not just make art and generate your students' essays. We're also interested in finding other areas to fly. So if you have an area that's infested with spotted lanternflies and you're willing to let me and my graduate students come and fly some drones around, that would be wonderful. I'd love to talk to you about that. And I always want to hear your ideas. So if you think that there's a better way that we could track or detect spotted lanternflies with autonomous robots, if you think there's a thing that we should be targeting, a place we should be targeting, I would love to hear that. And I'll leave you with that. If you have any questions, I'm here to answer questions. And if you have any data for me, please reach out. I'm very easy to find. Again, I'm a professor at Binghamton University. Here's my email, jboubin@binghamton.edu. And thank you for having me.
Sorry, I have the mic. So can you explain the data exactly that you actually need from us?
Oh, yeah. So that's a really good question. The data that we need, really, if you have pictures of spotted lanternflies, that is what I want. Just pictures. If you can tell me where they were taken, that would be even better. But really, just pictures of spotted lanternflies is all we need to train a real machine learning model. That's it. So if you have those, I would love them. And egg masses, yes, egg masses, sorry. Egg masses are really the more important aspect. So over all of the entire growth stage, the life cycle of the spotted lanternfly, egg masses are really what we want to detect because, again, they're stuck there for 6 months out of the year. That's the easiest thing for us to detect. Robots, generally, animals do not like, especially drones are very loud. I can't, spotted lanternflies are going to fly away from our drones, very likely. I mean, they fly away from you, they fly away from people. So we really would want egg masses, but everything would be beneficial to us.
So Jayson, just so that you're aware, over here, this way, there we go. Great presentation. One of the things that we get a lot that would be confusing for people that may impact your programming of all your machines, lichens, because they have very similar coloring and shapes to egg masses.
Yes. So one thing that we do is something called out of distribution detection. So that's a very common thing in machine learning now, and that is a very important aspect to references. We need to know things that might look like a spotted lanternfly, look like an egg mass, that we can then say, that's actually not that. We can give more of it to our model. So thank you. That is excellent information.
What format do you want the pictures?
Doesn't matter. I'll clean them and label them. I have students. Yeah, I don't care. As easy as possible. PDFs, JPEGs, PNGs, WebPs, I don't care. You can give me a video. Yes, I can make that available. Yeah, I have a Google Drive link that I can circulate. But yes, I can make this very easy for everyone.
We have time for one question online. I'll quickly ask it here from Ho Ping Lu. Spotted lanternfly adults can be detected by infrared camera. Any thoughts on using infrared thermography with drones?
Yes. So it's funny. I was just talking earlier. So I have a paper that I'm submitting in a couple days where we have a very nice result. We're getting some of the first real-time processing for full hyperspectral cameras on board UAVs. Hyperspectral cameras can detect infrared, near infrared. So yes, that is absolutely an avenue that is worth exploring. It's a type of camera that we can now process online in real time. We do have them in the lab. So if you have data on that, I would also love to see that. All right.
So I'm somewhat unfamiliar with all this UAV stuff, but is this like if you were to send a UAV out to collect these images that you're trying to get like through a railway, are you also able to collect other features like the structural complexity of like a forested stand, or is it just like when you send it out, is it like a one and done sort of process?
That's a great question. So when we collect data, so simultaneous localization mapping by necessity builds a point cloud. So what we're going to do is build a point cloud of these orb features. And so things like the tips of leaves and little points on a tree are going to generate to the point where we can actually see at least some of the structure of the tree itself or some of the structure of the rail line itself. We would export that point cloud. That's something that we can keep. Now, we don't always keep all of the data that we generate online with our UAVs, but that is something that is very maintainable. There's no reason that we can't keep that.
I also do know that there's a professor at Purdue, Dr. Songlin Fei, who's working on that exact project right now.
Thank you.
All right. Thank you very much.